My name is Buji. I'm a PhD student in the computer science department at the University of Wisconsin-Madison. And like I was introduced, I'm going to talk about basically the effects of your outer ear when used in spiking neural networks for neuromorphic speech denoising. So quick outline, I'm going to go over motivation for our experiments here in the beginning. Then I'll talk about our methodology, our training pipeline, what data sets we used. I'll talk about some key results in the evaluation section, and then I'll summarize with the conclusion and some kind of interesting and wacky ideas we're doing for future directions. Okay, so just to set the stage and give you a little bit of context, so the key goal with speech denoising is you're given this noisy input that contains some important aspects, namely speech, and some unwanted artifacts like noises that you're trying to remove. And deep neural networks have had a lot of success in this area in terms of being able to remove the noise from the speech, but they do so at these huge kind of large models that end up taking a lot of power and are hard to interpret because of their large depth. So here's a traditional flow that I show here that is pretty common in a lot of deep neural network models. You have your audio, you perform some transform, usually it's a Fourier transform or some form of like MEL spectrogram. You pass this input into your deep neural network, and then the deep neural network is able to produce something that can be inverted and recover the clean speech. Now, although they were originally inspired by neurons in the brain, I feel like deep neural networks have diverged quite a bit from the source material that is in the brain. And so we look a little bit more back to biology for inspiration here, and we look at the ascending auditory path, specifically the structures below the cortex, looking at the brainstem features. And we note that there's actually very few synaptic junctions as auditory is transduced from your outer ear up to your auditory cortex. And so I outline these here in the bottom figure here to kind of show the pathway that sound takes to get from the outside world into your brain. And you can see first it interacts with your anatomy, namely your outer ear. Then signals are converted into electrical signals in the cochlear nucleus or in your cochlea, and then they propagate to your cochlear nucleus, your superior olivary complex, your inferior colliculus, medial nucleus of the thalamus, and then up to the A1 area in the brain. Now I'm grossly oversimplifying. There's obviously recurrent connections here, but for the most part, it is very feed forward and it is very force structural in this case. So in existing works, looking at spiking neural networks in this area have gotten us some part of the way there. They really exploit this kind of like shallow nature of the processing in the brain. And I think this is, we thought this was a great starting point, but we noticed that this problem in general is pretty malformed because a lot of existing work don't take into account of these anatomical things that happen at the front end. So the key differentiating feature of our work is that we're modeling these outer ear effects of audio before they're even propagated into our shallow spiking neural network. And the end goal here is, of course, to get after some of the lower power consumption and high efficiency of the brain. Okay, so for our methodology, we rely on two open source data sets, the SIPC head-related transfer function database for head-related impulses that we can model sound coming from any arbitrary location. And then for our speech and noise data set, we rely on the Microsoft Deep Noise Suppression corpus. It's pretty good, pretty diverse corpus, including speech recordings from English, Russian, German, Spanish, and French. Our noise recordings also include things that are both biological, like a dog barking, or abiogenic, like the fan or a police siren going on. And we formulate these into 30-second clips that we feed into our network. Altogether, we have 500 hours in training, 500 hours in validation, for a total of 1,000 hours, about half a terabyte of disk space. Okay, so what does the flow look like? So I'm showing here these frequency transforms of input audio. So in the top, I show what the clean speech looks like. Here, there's 3 different speakers, and you can see that they have these unpredictable characteristics of having silent speech or silent portions where perhaps you're taking a breath between speaking. In the bottom, I show an example of the type of audio noise clip that we show. So in the first case, it's like rain. In the middle part, it's just static. And in the last case, it's the creak of a door opening. So the first thing we do is we augment these input audios with these Pinna cues, and these basically allow us to play ventriloquy with the sound and say that speech comes from here and noise comes from here, and augment our audio to have those artifacts. And you can see that this directly affects the audio as well. Then in an additive process, we synthesize the two together. We feed this into our shallow spiking neural network model. Here we're using the Intel Lava deep learning library to have like this 4-layer network of sigma delta neurons. This produces a multiplicative mask, which we then apply to the noisy audio to an attempt to get the clean signal back as our recovered speech. Okay, so I'm just going to highlight a couple quick things about our results, or key points from our results. So first, obviously, we want to see what is the effect of the Pinna alone on speech before we get into any of these neural network models and whatnot. So on the vertical axis here, I'm varying where we put speech. On the x-axis, I'm varying where we put noise. And brighter colors represent better denoising areas. So naturally, you see a good portion in the bottom right, because this is the case with speech is in front and noise in the back. Pretty intuitive. The converse is also true. When you put speech in the back and noises in the front, it's really hard to focus on the speech since it's now being occluded by your Pinna. When we feed this into our spiking neural network, we see some pretty interesting patterns that kind of emerge. So first, of note, our good portion is still pretty much there. It maybe have moved a little bit, probably effects of the Pinna. But we also see this region of bad performance on the correlated diagonal. And this kind of intuitively makes sense because if you think about it, if speech and noise are coming from the same portion, it's really hard to distinguish the two, as a human. We also saw this weird kind of oddity here on the anti-correlated diagonal. If you're interested, there's more details in the paper. But this is all, we had some good results, but it's kind of obvious that we had good results because now we're like, presenting our network with these input audio that's been enhanced with ways to make it easier to extract speech. And so we wanted to remove kind of some of these harsh constraints and make our network able to determine or get good speech denoising when speech and noise are in arbitrary positions. So that's what the fixed position results are shown in the green line, which is where we got that good result when speech is in front. But then we tried randomizing where speech and noise can come from, and we see that that significantly confuses our network, which is what's shown in the red line here. So to get away with, or to understand this a little bit better, we performed a bunch of directed case studies to try to understand where is the spatial temporal receptive field where putting speech is optimal for, and putting noise is optimal for achieving the speech denoising task. And so there are more explanation of the detailed results in the paper, but I just wanted to highlight something that was kind of interesting that we were able to examine in our network. So one of the main parameters of our network is this axonal delay parameter at the end of our neuron, which helps correlate temporal frames of the speech. And we noticed that in our best performing network models, this parameter is actually increasing. And what this means in terms of like physical terms is that our neurons are looking at wider context windows. And so even though this is a pretty small context window, we see that our networks, when enhanced with these spatial cues, are better able to correlate things in time. And so that's kind of our key takeaway from where this work may lead in the future as well. So our networks can focus on these like sub-phoneme features, which are very quick and immediately detect that someone's speaking and that there's noise coming from somewhere else. So in conclusion, we've kind of shown that shallow spiking neural networks are efficient in this case, both in terms of model size and in terms of performance accuracy. Again, they're able to stand up to some of the state-of-the-art models that we compare to. And our hope is that they're a little bit more interpretable than these deep CNNs because we're hopefully mimicking and maybe presenting a starting point to try to understand the workings of the ascending auditory path. I also want to mention that I'm a big proponent of open source work. So all of our flows are like cloud ready via GitHub and Docker. So if anyone else wants to play around with these things, you're welcome to do that. You just need a GPU. And in future work, we have a lot of cool directions, namely monitoring the binaural audio path in the ascending auditory pathway. So like modeling how things decussate and how signals can cross over between left and right hemispheres. We're looking into like how can you come up with the optimal 3D shape for an outer ear for speech denoising. Some other audio tasks that we're interested in is like fundamental frequency estimation, sound source localization, and we're actually building this neuromorphic audio foundation model that we're hoping will have some good results, though we don't see anything good yet. On the meta study side, we're kind of also looking at like how do we improve SNN training in general on GPUs? Because we found that when we were training our networks, it was really slow on our GPU cluster. And so we're looking into both software and system level optimizations there. And lastly, we're really hopeful to get our hands on edge compute hardware so that we can actually do the energy and latency evaluations for inferencing for our networks. And with that, I just want to thank my advisors, Professor Mika Labasti and Professor Joshua San Miguel. And I'd also like to thank the Center for High Throughput Computing for providing access to the GPU clusters. And that, thank you. So my goal in the end is to hopefully develop spatial audio tasks as the killer applications for neuromorphic domain, definitely lofty. And I don't know that this is even the right place to start, but it seems like it might be. So thank you.